This should have that segregation. Just look. No, this is only the coding region.
Yeah, that's just 365.
Okay,
But
yeah, maybe that will have.
Okay, one sec. Yeah, this one has it.
Yeah.
So this is, the coding region, the exon, intron. So all these are mentioned in the GenBank database itself. So you can actually use this information to figure out how to actually, if you want to partition your data set into different domains, you can actually do that. So maybe if we have time today, I can show how to actually segregate it into domains.
I think we have given them protein data set also probably, right? And and here you can see that exon. So this gene has 2 exons. Exon 1 starts from in this the sequence. It starts from site number 4 till site number 277, and then you have exon 2 that starts from site number 438 and it ends at 475. So if you go all the way to site number 475, you will notice that there's a TAA at the end somewhere, and in between is the intron. So once you have generated, say if you have generated the protein sequence, you align it with the available sequence, and then you can figure out where the exons and introns are. And then in Mega, if we have time, we'll show you how to actually select those domains or mark out those domains.
Okay, is my slide visible?
Yeah.
Okay, I'm just going to check if we have everyone on board. There are still some people missing, but yeah, if I hear someone, then I'll probably minimize the window and let them.
WhatsApp if required. So I think there are 2 people short.
Okay. Okay, so we'll start off. Okay, can you see the pointer?
Yes.
Okay, all right. Okay, so we will switch gears now, and we'll talk today about models of sequence evolution. So till now, what we have been doing is basically, you have the sequence alignment, and then we get into the pairwise genetic distance, and from there we make the tree. Which so for the tree building methods that we have done till now is UPGMA and NJ. So we've basically gone from this to this and then the tree. So and we count up the number of differences, right? So for example, between gorilla and chimp, there are 5 differences, and between gorilla and human, there are 4 differences, and we take this into account and go ahead further. So we either do a rate corrected distance, or we choose the lowest number of differences, and then we go ahead. But so let me introduce you to this new terminology here, which is called P distance. And yesterday, while Chaitanya was doing a session on Mega, he actually showed how to get the P distance. So the whole idea of this presentation is that often you will realize that it's not enough to just get the number of differences between 2 species. you often have to actually estimate the number of differences there are, or how different two species are. So before we go ahead any further, from now on, we will be using this thing called p distance, which is nothing but the number of differences between a pair of sequences divided by the total length of the sequence, right? Okay, so just for an example, let's say there are 4 species, S1, S2, S3, and S4, right? And the total data set is 20 base pairs long, right? So between S1 and S2, there are 2 differences. So there's one change here and another change here, right? And if you want to find out the p distance, so it's the total number of changes divided by the total length of the sequence. So that will be 2 divided by 20, right? So that will be 0.1, right? And this is actually a better representation of um, the differences between species pairs, largely because, let's say you're taking different genes, and if you have a bunch of species and you have data set of different genes, so you take gene number 1. If you have to explain how different two species are, if you have gene number 1, it doesn't make any sense for you to say, okay, between these 2 species in gene number 1 there are 2 differences, in gene number 2 there are 5 differences, or gene number 3 there are 10 differences. Whereas it makes more sense to say that, okay, in gene number 1 there is 10% difference, so 0.1 is 10%. So so that way you can actually, so it's also normalized, apart from being a good representation of how you can actually compare between different data. Another reason why p distance is much better than just finding out uh, only the number of differences between a species pair is that it takes into account missing data, right? So for example, here between S2 and S3, you only have this overlapping region, which has in which data can be compared, whereas there is missing data here in S3, and there is missing data here in S2, right? So you take only this into account between S2 and S3, find out the number of differences there are. For example, between an S2 and S3 here, there is how many? There is one change here, and you divide that with only this overlapping region rather than the complete data set. So that will be 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that will be 1 divided by 9, and that should be 0.11. Yeah, so that will be 0.11, right? So this is definitely a much better measure than just finding out the number of changes between 2 different species. Any questions here in p distance? Because this is what from now on we're not going to be working with uh, observed distances. We are only going to be working with p distance.
Hi, sir. As you have told in the second portion, means S2 and S3, there is an overlapping sequence, and if we continue the 2 species pairs, and if we get another overlapping sequence, we will add up that too, sir.
Correct.
Okay.
So we will add only the part that is overlapping between these 2 species.
Okay.
So for example, between S4 and S1, we take this part and we take this part. So this is the overlapping region, this is the overlapping region, right?
Okay.
And you just take how many ever differences there are in this.
Okay, thank you.
All right. So here is a question. So you have this should be fairly easy. Let's say these are 2 different species, and these are sister species. So what is the total number of differences between them? How many differences do you see?
Two differences.
Two differences, right? Okay. So then what would the p distance be?
0.2.
Correct. Okay. So you have your pairwise genetic difference is 2 because you see two changes here. So your genetic distance d is basically 2 divided by how much ever the length of the sequence is, and then you basically get 2 substitutions. So you're very happy you've got this. Now let's say you have a time machine and you go back in time and you find out the common ancestor of these two species, right? And you sequence that common ancestor, and the common ancestor has this sequence. Now, how many changes do you think has occurred?
Only one. Total 3 different changes.
Total 3 changes, right?
Yeah.
So between in different lineages, there are different changes that have occurred. So along this lineage, there is one change that has occurred. So this G has remained as is, whereas this G has turned into a C here. Whereas here, this G has turned into a C here, and this G has turned into an A here. So what you realize is that only along this side, there have been multiple changes, right? So we know, I mean, because you've gone back in time and you've actually looked at the sequence of the common ancestor, now you can say that there are three changes that have occurred as opposed to 2 changes, which was your initial answer, right? And if you realize, every change that happens, so with every change that happens, all the earlier changes are lost. And you can actually think of various different combinations of how these changes occur. For example, some changes might actually make them similar, other changes might actually make them different. But the problem is you're looking at them today, so you won't be able to know how many changes have really occurred. And therefore, there's generally a discrepancy between your observed distance, which is right here, and your actual distance, which is on this part, right? So you can have various different scenarios. Let's say the ancestral state was a G, and along one of the lineages, it has remained a G, whereas in another lineage, in the other lineage, it has changed to a C. So your actual distance is 1, and your observed distance is 1. Everything is fine here. But here's another scenario. So you have the ancestral state as G. So along one lineage, it has remained as G, whereas here, it has first changed to an A and then to a C. Right?
Sorry to interrupt, Aniruddha. Can you just repeat again? I just lost my internet connectivity.
Okay. From where do you want me to repeat again?
Just starts from after this 2 substitution thing. The ancestral speech.
Okay, so basically, what has happened here is that when I asked you to tell me how many changes that has occurred between these two species, the answer was 2, because you see 2 changes here, one change here and one change here, right? But when you go back in time and let's say you find the common ancestor of these 2 species and you sequence it, you realize that there have actually been 3 changes, which is 1 change along this lineage and 2 changes along this lineage, right? So on this side, there have been 2 changes, right? And what I was getting at is that you can actually have various different combinations of such changes. So you can either have a G remaining as G here, and this one changing to a C. So which doesn't really affect your actual distance and observed distance because they're both record 1. Whereas here, in reality, there are 2 changes that have occurred. So your actual distance is actually 2, but your observed distance you see only 1, right? Because the earlier change is masked, right? Now this is another scenario where again this lineage, it remains the same. So this G changed to a C at some point, and then it changes back to a G. So this is called as reversal, right? You can also have a scenario where you can have very similar kind of states that have attained from this particular state. So this might look very similar to convergence, but remember that in convergence, you're talking about uh, independently evolving states from completely different ancestors. But here you have the same ancestral state. From the same ancestral state, independently, 2 different states have evolved, right? So there's a T here and there's a T here. So this is called parallel evolution. So the problem with here is that your observed distance is 0 because you don't see any change today. But in reality, 2 changes have occurred, one along this lineage and one along this lineage. You can also have another scenario where the G changes to a T here and the G changes to a C here. So your observed distance is 1, whereas your actual distance is actually 2. Right? So you can think of various different combinations like this. The whole point being that you're looking at the sequences today. So any changes that have happened before this are masked, right? And therefore, your actual genetic distance might be either greater or equal to the p distance, your observed distance that you get, right? So the actual genetic distance, which is d, is your p plus the hidden changes, right? And what we do using these models, these DNA substitution models, is that we try and estimate uh, the actual genetic distance based on the data set that you have, right? Okay, so this is what is really happening. Now, let's say you have 2 species. Actually, let's go back to the earlier slide where you have these 2 species, species 1 and species 2. And let's say we go back in time, which is just before these 2 species had started separating. And then you basically cut this into multiple slices of time, and you are looking at what the sequences are or how the sequences are evolving along both these lineages, right? So what will happen is that with more time, you will have a greater p distance, right? Your p distance will keep increasing as and when your time increases, right? So this is what you would ideally see, which is the p distance starts from 0, and then remember that you're looking at these 2 sequences. So your p distance starts from 0, and then it starts increasing, right? And this is what you would ideally see, but it won't be it won't keep going up. It will saturate at some point, right? Can anyone tell me why it will saturate?
Aniruddha Jayaditya here.
Yes.
I'll just try. So if either the species on the process of mutation and evolution, because of mutation, either it will go to a state
where where it has accumulated too much of bad sequences and get extinct?
No. So you're talking about species that are not extinct. So you have
Okay.
two different species, but I'm saying that if you just keep tracking them, tracking how the sequences, the p distances change over time, you will realize that it will not be complete 100%. It will saturate at some level.
So, Anirudh, this is Shivam here.
Yeah.
Yeah, so I think this is because the two different lineages or any lineage which we are talking about, they have one set of nucleotides, and whatever permutation or combinations you see, at one point they'll finish off. Is it that?
Correct. Yeah, absolutely right. So basically, you have, I mean, another way to look at it is that you have only four bases, right? You have A, T, G, and C, right? So you start off with these two sequences. Okay, wait. So somebody is, I think, trying to gain entry. Okay, so you have only four bases. So you start off with these two sequences being very different from each other, right? And then the p distance keeps increasing. But at some point, some difference, some of these, so because these are constantly mutating, some of these changes will make the two sequences different. The other changes will actually make them similar. So it will actually saturate at a certain point, right? Okay, so here's my next question. At what point do you think it will saturate? I mean, I've already given the clue because there are four bases. There's A, T, G, and C. But at what point do you think it will saturate? Any ideas?
When we reach the maximum possible combination, the observed combination.
When can we reach the maximum possible observed combination?
I don't know. 4 to the power 4, maybe 64. I don't know.
Sorry, I didn't get that.
When they're separated fully.
They are still separating. I mean, they're completely two different species. So I'm just saying, that these are two different species, but the p distance will never be 100% different from each other. They will always saturate at some point. And the clue was that there are only four bases.
I hope everyone understood the graph here, what is going on, and the question that Roy asked. With time, you have p distance between two species. Ideally, we would expect it to reach 100% difference, but it saturates at some point in time. And where will it saturate?
Is it 4:4?
Is it, what do you mean 4:4? Okay, so let me just imagine a scenario where our Krishna Chaitanya very lovingly comes into your room, and while he holds on his hands a tray which consists of 4 TT balls, right? And these 4 TT balls are named differently. One of them is named A, the other is named T, then there is a G, then there is a C, right? So there are 4 TT balls that Krishna Chaitanya is holding, and he gives it to you, right? Now, my question to you is, what is the probability, if you put your hand inside that box or the basket, what is the probability that you will pick any TT ball?
100% probability.
100%.
100%, right? Okay. Okay. So what now? You pick out one of the TT balls, right? And you look at it, and it turns out it is a T, right? So you're like, okay, this is a T, and then you put it back. Now, what is the probability? You put your hand back in there. You've put the T back. Now you put your hand back in there, and you pick out another, or you pick out a TT ball again. So what is the probability that it is T again?
0.25.
0.25. And so then you can ask yourself the question, what is the probability that it is any other ball other than T?
0.75.
0.75. So 0.75 is where it will saturate, right? Because you remember there are only 4 bases. So some changes will make these sequences different. The other changes will make it similar. But then the fact that you have only 4 bases, you have only 0.75. I mean that you can saturate at only 0.75, right? So tell me something. So can it be less than 0.75? So we've made an assumption here that any base can change to any base, right? So that is an assumption that we have made.
Yeah, I think it's possible.
Okay. Why do you think it is possible? Under what circumstances?
Because it's the gene who decides it has to mutate or not. 0.75 is the maximum and minimum that the gene will decide.
Okay. So what if it is a gene under selection? Do you think it can still be 0.75?
I don't think I get this question.
Okay, so let's say that you're tracking how this gene, the p distance is increasing in this particular gene, right? So this is your observed p distance in a particular gene, and you find out that this particular gene is not under selection. This is just some nuclear neutral gene, right? So it is not under any evolutionary force, right? But say you were tracking the p distance in a gene which is under selection. Basically, there are some evolutionary forces acting on it, so that there can't be many changes. Did everyone understand the question?
If there are no changes going to be there and this is the condition, then how can it change? It won't be
So
more.
there is going to be change which does not change its does not change its protein structure.
Okay.
Okay. So now, what do you think might be? At what point do you think it will saturate?
Now I think we should look at the third base or something.
Correct.
Okay.
So for a protein coding gene, it will saturate at much lower here, because most of the times when you're talking about protein coding genes or genes under selection, the changes in the third position are mostly silent, right? So there can be a lot of changes in the third position, but that will not change your amino acid. That's not always true, because there can be changes in the first position also which are silent, but by and large, this will saturate at 0.33 of 0.75%, right? So now the problem here is that if you have two different species that have diverged from each other long time ago, right? And they fall within this particular region, right? What is going to happen is that if let's say you're taking a neutral marker, what is going to happen is that all these species are going to be 0.75 or 75% different from each other, right? Or 0.3 or 33% different from each other. And if you have a bunch of species that are all 75% different from each other, you won't be able to build a phylogeny, right? So therefore, in order to correct for these issues or to correct for multiple hits or these changes, you need models of sequence evolution. So what we'll do is we'll start off with the most simplest model of sequence evolution. Please stop me at any point you think it is becoming unclear. So there are, yeah.
The point which you just explained right now, why we can't make a phylogeny.
Okay, so
point was unclear.
Yeah. So when you're building phylogenies, you build phylogeny based on variations, right? So when you have a bunch of species that are equally different from each other, so all the species are 75% different from each other. There is no variation between these species. I mean, all of them are similarly different from each other. So therefore, you will now not be able to build a phylogeny. Does that make sense?
Yeah, it does, definitely. Thank you.
Yeah, and another way of looking at it is, when we calculate the distance matrix, pairwise distance matrix between species, and use that information to build UPGMA tree or neighbor joining tree. In that distance matrix, every species pair shows the same distance. Then how do you even start? Right? What species pair do you put together first? So that is the problem.
Okay, yeah, correct. Yeah, I get it. Thank you.
Okay, so we'll start off with the most simplest model, which is the Juke Scanter model. And all these models come with their own assumptions. So Juke Scanter model assumes that all substitutions are equally likely, which is basically saying that an A can change to a T can change to a G can change to a C, or vice versa. Any base can change to any base, right? And then it also has another assumption that there is no among site rate variation. Now, this basically means that you have 3 positions in a codon, right? So it's saying that all these sites, there is no variation in all these, the rate at which the mutation happens in all these 3 sites, right? And I mean, of course, I'm sure you realize that this is unlikely, but it's a nice base to start with. It's a nice model with simple base, simple assumptions to start with, and from there you can start getting more nuanced. Now, as a result of these 2 assumptions, there is also a third assumption, which is the base frequencies are in equilibrium, which means that you'll have equal number of A's, T's, C's, and G's, right? So there'll be, if you so for example, if you just take one string of A's, now remember we're talking about one single sequence here. We're not talking about we're not comparing 2 different sequences, right? So yeah, let's take a single sequence which has a string of A's, and let's say it evolves using following a Juke Scanter assumption. Then what you'll have is equal amount of A's, T's, G's, and C's after millions of years. Okay. Another assumption of Juke Scanter is that it is a reversible model, right? So when I say it's a reversible model, it means the probability of change from any base to another base. So for example, here, probability of change from A to a G is equal to probability of change from G to an A, right? So so this is again probability of change from A to a G, probability of change from A to a T, probability of change from A to a C, right? And this probability of change from one base to another base given a particular time is also called Pij given time t. Okay, so remember this will come up again when we deal with likelihood. So Pij given time t is the probability of change from one base to another base at time t, right? So all of these are Pijs. So any base changing to any other base is Pij. And remember, all of these are equally likely. And then because Juke Scanter is a reversible model, even this is Pij, right? So all of these are equally likely. There's also a probability of no change at time t, which is probability that the base remains the same, and that is called as Pii given time t, right? So all these are Pii. Okay, this will be clear in a moment, but just remember that this will keep coming up when we deal with likelihood also. So now we've gone into probabilities. Okay, there are a few more terminologies that we need to learn. One is probability of no mutation, which is given by e to the power of minus v. And the probability of mutation is 1 minus e to the power of minus v, where v is basically your mutation rate times time, right? And if you think about it, your probability of no mutation actually will decrease as and when time increases, right? So if you have generation or time in terms of generations, the more time passes, the more is the probability that your e to the power minus v will decrease, right? So there are more possibilities of mutations occurring. Does that make sense? Okay, I'm assuming it makes sense. Okay, yeah, somebody has a question. Okay, so we actually have to, so I'm not going to derive how we actually get this PII and PIJ, but I want you to remember these formulas. So the PII given time t is 1 by 4 plus 3 by 4 into e to the power minus v, right? And Pij is 1 by 4 into 1 minus e to the power of minus v, right? And remember, today I had actually given you, I had attached the phylogenetic handbook with you. So if you go through chapter 4, it will have all the detailed information that you need about how we've actually come to get this particular formula. But as long as you understand that Pij is basically change from one base to another base given time t, and that is given by this, and Pii is the base, there is probability of no change given time t, and that is given by this, we are good, right? But also remember that this is you're looking at it only in one sequence. You're not comparing sequences yet. You will compare sequences right here, right? When you look at two different sequences, and this whole circus that we're doing right now is basically to find out your genetic distance or this is basically assuming all the assumptions that are there in Juke Scanter, right? And the only thing that you have to put in this is P. Your P is basically your genetic distance, right? And this is the corrected genetic distance, assuming Juke Scanter. All right. I know this can get a little bit heavy, but just bear with me here. Yeah, somebody has a question.
Roy, can I just interject for just a minute?
Yeah.
So basically, what we are doing here is, as Roy pointed out, using P distance is not a good idea in situations where the species are distantly related, because then all the species will pretty much show the same P distance. So we have to correct for multiple hits, multiple changes. And the way we do that is by using models of sequence evolution. Roy just went through the simplest model of sequence evolution, Juke Scanter. And this formula that we see here is correcting for multiple hits using Juke Scanter model of sequence evolution. So the D there is the estimated distance after correcting for multiple hits, and that's why you have -3/4 inverse of -1 by not inverse, log of 1 - 4/3 P, and where P is your P distance, right? So to estimate the actual distance between two species, this is the formula you use. You just calculate the P distance, plug it into this formula.
Okay, so so you remember the assumptions, the basic assumptions of Juke Scanter was that any base can change to any base. Right?
Roy, hang on. There was a question.
Okay.
I can't see the question now. Wait.
I'm going to read it out for you. So the question from Shruti is, how far in the ancestry does P distance start giving errors? Like, for example, within same genus or same family?
How far in the ancestry? So you're basically, so you remember the node, right, that we showed yesterday. So let's say you start from that node, right where two different species have started diverging, right? So we're talking about the P distance from there onwards till what we see today. Does that make sense?
Yeah, I think Roy, so another way of looking at it is, P distance. P distance becomes a problem right from the very beginning, but it's less of a problem. This is another way of looking at it. It's less of a problem when the two species have just diverged, and becomes a bigger and bigger problem as they diverge more and more.
So Roy spoke about saturation, right? I hope all of you understood the saturation part. So the moment saturation starts happening, that's where your problems start with using just P distance, right? We have to start correcting for saturation ever since then. And when will saturation happen? We really can't say. It really depends on how fast that gene is evolving, and like what Praveen said, it also depends on when the species or the individual you're using diverge from its from its closest sister, right? So the answer to that question is we don't know. We can't be accurate about when P distance starts giving starts showing saturation. And that's the reason we have models in the first place, so that we correct for this kind of saturation. Go on, Roy.
Okay. Are there any other questions? Because I can't see the chat box.
no other questions. You can go on.
Okay. So, like I was mentioning, the basic assumptions that this simplest model that we have dealt with right now, which is Juke Scanter, the basic assumptions that Juke Scanter has is that any base can change to any base, and there is no among site rate variation, right? Now, turns out, if you look at the genetic code, transitions are more likely than transversions. So an A to a G and vice versa, or a C to a T and vice versa, are found much more in nature than an A to a C or vice versa, or G to a T or vice versa. In fact, in nuclear DNA, transitions are generally 2 to 4 times the number of transversions, and in mitochondrial genes it is even more. Right. So this is another. This is another point that a different model called Kimura 2 parameter model takes into consideration, which is that transitions always are more than transversions, while still assuming equilibrium based frequencies, which is equal number of A's, equal number of T's, G's, and C's. And so the transitions here are, there are 2 parameters, remember. One is transition, the other one is transversion. So the transition is called alpha, transversion is called beta, and therefore you have a Kimura 2 parameter model, right? So the assumptions here again are equal base frequencies, so equilibrium base frequencies, equal number of A, T, G, and C, and again no among site rate variation, which is very similar to what Juke Scanter does. But the main difference here is that it weighs transitions more than transversions, and this is what the correction looks like, right? So it's not just incorporating T distance anymore. You actually have to estimate the transitions and the transversions, and then get a corrected genetic distance, estimated genetic distance, given this particular model, right? So as you can see, it's getting, we start off with a very simple model, and then you can start adding more and more complications. Now, if you actually look at, so till now we have been assuming that there are equilibrium based frequencies, right? Which is that there are equal number of A, T, G, and C, right? But you will realize if you look, even if you just look at the cytochrome B data set that we have given you, which is 1140 base pairs, you will realize that there aren't actually equal number of A, T, G, and C, right? So although you would expect, given the assumptions that Juke Scanter or Kimura 2 parameter has, you would expect that all of them would be 25%. You would realize after checking these is that it's not actually 25%. So one of them is 24.9, the other one is 34. There's also that can also go as low as 12%. So this is also another parameter that one of the models can use, which is that there is unequal base frequencies, right? So for example, a model called Felsenstein 1981 assumes multiple hit unequal base frequencies, but all substitutions are equally likely. So similarly, you will have a lot of different models. The most complex one being GTR, or General Time Reversible model, which has, so remember we started off with only one parameter in Juke Scanter. We had 2 parameters here. We again have 2 parameters here. So GTR has 6 parameters, right? So any change from one base to another base is a parameter in Juke Scanter, right? Now, Another assumption that most of these models make is that the substitution rates across all the sites in the codon are homogeneous, which is unlikely, right? So therefore, I'm sure most of you have seen that there are models called GTR plus gamma, right? So that gamma is basically it's alpha. It's a shape parameter that can attain different gamma distributions based on the data set you have. So this alpha is, by the way, it's different from transition. So remember, in transition and transversion, that was called alpha and beta, but this is a different alpha. This is a shape parameter, right? And it can actually attain different gamma distributions. So when you have an alpha which is less than 1, there is strong among site rate variation present in the data set. So for example, you have alpha of 0.5 here, which means that most of the sites have low substitution rates and very few sites have high substitution rates. Right? So if you assume something like a Juke scanter, the alpha value is going to be very high. For example, alpha, so this would be Juke scanter, where all sites can mutate at a very, very high rate. Right? So this is what you mean by a gamma parameter. So when you say GTR plus gamma, this is what is meant. There's also another variant that you can add, which is invariant sites. So you can have, so you can say that some sites are not very variable, right? So that can also be another parameter. So therefore, you can have something as complex as GTR, which has 6 parameters, plus a gamma shape, plus gamma, plus I, right? Okay, so thankfully, we don't have to, manually select these models. So there are programs that actually, where you can actually feed in your data set and they find out what model fits your data best, right? So usually, the more complex model fits the data better, but obviously the analysis will take a lot of time. And also remember that there are things like so just because GTR has a high number of parameters, it doesn't mean that that is always going to be the best model for your data set, right? If your data set is really small, you might run into issues such as underfitting or overfitting, which is basically you have too many parameters given a small data set, right? Okay, so if there are there any questions at this point?
The GTR model has already included the substitution rate or what, sir?
Yes.
Then why should we add that gamma part to the GTR? GTR plus gamma. We have seen that GTR plus gamma.
Yeah.
Then
so
already
the gamma, the gamma is for among site rate variation. So that gamma shape parameter is only to show that between sites, the amount of variation or the mutation rate can or cannot be homogeneous.
Oh, among the sites.
Among the sites, correct.
Oh, okay, fine.
Could you explain the shape parameter?
Oh, actually, I don't understand these gamma shape parameters completely. Raveen, do you want to talk about it?
Yeah, sure. Yeah, so basically, this this graph here shows in a alignment how is nucleotide rates of nucleotide substitution distributed, right? If you have a situation where, for example, you're looking at a gene, then we know that third position of the codon is more likely to change, but the first and the second position is less likely to change. So in that situation, your alpha would be less than 1, because you'll have a few sites, only the third position, that are changing rapidly, and the rest of them are changing more slowly, right? Whereas if you have a situation where you are looking at a neutral marker, so this is a marker that is not under selection. So every site is free to change, and the rate of change at every site is the same. So there is no among site rate variation. Then this parameter will capture. I mean, the alpha value of more than 1 will capture it better. If you look at the alpha value of 100 here, it's basically saying that all sites have the same rate of change. So you can have, depending on your data set, you can have, all these scenarios between these two extremes. One extreme is a neutral marker. Okay, sorry, that was lightning and thunder. I hope people can still hear me. So you have two extremes, neutral markers, where all sites are evolving at the same rate. Your alpha will be more than 1. And then you have the other extreme, where you have few sites evolving rapidly, the rest evolving more slowly. You'll have an alpha value of less than 1. And you'll have other markers that fall in between. And each of those distributions would refer to those scenarios. Okay, and yeah, we need to incorporate, and some of these models actually incorporate this correction while calculating genetic distance. This is important because sites that are evolving more rapidly are more likely to experience multiple hits, and they must be treated differently. And that's why we need gamma correction. I hope that made sense. I mean, as long as you understand, why this is important, I think that's good enough. How exactly it is done, none of us really understand. It's very, very mathematical.
So do the genes that is undergoing a high substitution rate will have a high alpha value?
No, they'll have low alpha value, no? Because genes, basically, as I said, if you pick any gene, it shows among site rate variation. High alpha value is good for a marker that is not showing any among site rate variation. Right? High alpha value is for markers where every site is evolving at the same rate. Whereas genes, by definition, are under selection, and certain sites are evolving more rapidly than others. So there is among site rate variation. So that's when you use alpha of less than 1. Of course, the program will figure out, what is the alpha value for your data set. You don't have to do it yourself. Does that make sense?
Okay, thank you.
Sir, each model has a substitution rate as standard substitution rate, no, sir? Then why should we include the gamma parameter to that? which means in GTR model already there is a fixed substitution rate. It is given a fixed substitution rate. Then why should we again add the gamma parameter?
No. So, for example, what GTR is basically saying that change from A to a C, A to a G, A to a T is different. Okay. Similarly, T to a G, T to a C, T to A is different. But it is not going to tell you whether there is difference between sites in these substitutions. For a given site, it's going to say that the rates are different, and it is going to take that into account while calculating, while estimating genetic distance. But it does not take into account between sites or across sites variation.
Okay.
Does that make sense?
Okay, sir.
Yeah.
Are there any other doubts? Okay, so if there are no other doubts, then we will move on to parsimony. We will actually move on to till now we've basically been doing a distance-based approach, right? Where we have gone from the sequence alignment to the pairwise genetic distance, and from there we've got the tree. So what we'll do now is a character state approach, where we'll deal with 3 different tree building methods: maximum parsimony, and tomorrow we'll do maximum likelihood, and day after tomorrow we'll be doing Bayesian inference, right? And these are definitely far better than distance-based approach, because there is no intermediate step, right? So you're going from your sequence alignment directly to your phylogeny, right? So in a way, there is no loss of information. And these character state approaches are also called discrete methods, because each of these sites is taken as a discrete unit, right? Where each site can have 4 different states. They can either be A, T, G, or C. And what you're doing at the end of the day in a character state approach is that you're reconstructing the evolution of each site on a tree. You'll also realize that till now you've been doing in the distance-based tree building methods, you've been working with UPGMA and NJ, and both these methods actually spit out a tree, whether you like it or not. Whereas in character state approach, you'll realize that we're actually going through all possible trees to find out which among these is the best given your data set. Okay? So we'll first deal with maximum parsimony, and a parsimony tree is a tree, or the maximum parsimony tree is the tree that requires the minimum number of nucleotide substitutions in order to explain the changes that you see between the sequences, right? So in other words, it follows the principle of parsimony, which is basically reducing the number of events, evolutionary events or evolutionary steps, in order to explain the character distribution. That you're talking about your data set here when I talk about the character distribution, right? So parsimony here is the principle of endorsing the simplest explanation that covers a case. And given 4 taxa, you can actually have 3 different unrooted trees, right? 3 different unrooted trees, assuming there are these branch lengths don't mean anything. So you can have 3 different unrooted trees, right? So assuming branch lengths don't mean anything, can anyone tell me how many rooted trees you can actually have? Okay, so how many places can you actually root the tree?
5.
5, right? So how many trees will you end up with if you have 3 unrooted trees? How many rooted trees will you end up with?
15.
15, correct. So yesterday somebody was asking a question that why are we not dealing with rooted trees from the beginning? So this is your answer. So you basically start off with unrooted trees. So because you have less number of unrooted trees, you can always root them later. And you can either root them using midpoint routing, or you can root them using outgroup method, which is the more preferred method. Right. So for this exercise, we'll be using this same data set that we have been using till now for UPGMA and NJ. Right. So you have human, chimp, gorilla, and orang. Okay. And remember that this is a character state approach, the discrete method, which takes every site separately into account. Right. So how does it do that? So so basically for every site, it is going to, given a tree topology, it is going to see how the characters have evolved. Right. So what we have here is, remember, we have 3 possible trees, right? Where one of the, let's say tree 1, you have human and chimp sisters, gorilla and oranga sisters. Tree number 2, you have human and gorilla sisters, chimp and oranga sisters. In tree number 3, you have human and orang sisters, and chimp and gorilla sisters. So let's take tree number 1, right, where human and chimp are sisters, and just map these particular characters on the terminal nodes of the tree. So this, by the way, is just this character, right? So there is a G in human, there is a C in chimp, there is a C in gorilla, and there is a in orang, right? So we don't know what this is, we don't know what this is, right? So this could be either A, T, G, or C, or this could be A, T, G, or C. Now what we'll do is we'll use principle of parsimony, find out what days is the most likely here, or the most logical to here, for here, for this node. Okay, so we can actually try various different combinations, right? So this is again, so we've gotten rid of the taxa names. So remember that this G and C here is actually your character, right? So you have G here in humans, and C in chimp, and then C and A, right? So what you can do is that you can assume that this node must have been a G, right? Because there is a G here, and this node must have been an A because there is an A here, which means that there would have been one change here from G to A. There would have been one more change here from G to C along this lineage, and one more change here from A to C along this lineage. So in total, we have 1, 2, and 3. 3 changes given this character distribution, given this tree, which is tree number 1. Right? Similarly, you can try out various other combinations. Right? So here we have the combination that we've used is G here and A here, and we've ended up with 3 different events that explain this character distribution. Right? You can try and put a C here and a C here, which means that this event is not necessary because there is no change right here. Whereas along this lineage, the C has changed to a G, and along this lineage, the C has changed to an A. So you have, so given this character distribution and C here and C here, this can be explained using 2 different events. Okay. So similarly, you can actually try out various different states for this particular node and see which of them has the least number of events. And you'll realize that it is this particular distribution that has the least number of events, which is 2. Right? Now, similarly, you do it for all the characters. So what we have done is only for character number 1, right? And the least number of events we have got for character given a particular tree, and this character distribution is 2 events. Now I take character number 2. Now character number 2 is very easy because it's a conserved character. So all the species have this particular character, which is T. So therefore, it's a no-brainer. Any other character would increase the number of events. So this being a T and this being a T will make sure there are no changes, right? So there are 0 changes in this. So you do it for all the other characters. So character number 3, character number 4, 5, 6, 7, 8, and until you reach the last character, which is 9. Right? And you remember, you're still doing it for tree number 1, where human and chimp are sisters and gorilla and orang are sisters. Right? And for each of these characters, you are noting down the minimum number of events that are required to explain this character distribution given a tree. And you add this up, right? And if you add this up, what it gives you is the tree length, right? And you can actually map it. You can actually map based on how many changes have occurred along each lineage, right? And this will give you your tree length given this particular tree topology. But remember, we've just this is just one of the tree topologies that we've tested. There are 2 other tree topologies that we can actually test this on, right? Which is where human and human and gorilla are sisters, chimp and orang are sisters, and here human and orang are sisters, and chimp and gorilla are sisters. And we've done it for all of these. Turns out tree number 2 and tree number 3, which is these 2, can be explained given this particular tree topology and the character distribution. They will have a minimum of 11 changes, right? So therefore, our most parsimonious tree is tree number 1, which can be explained using 9 changes. Does that make sense? Any doubts still here? Crystal clear. Okay. Now that we have the tree, and we also have the number of events that have happened along each lineage, we can actually scale the branches based on the number of events. So obviously this will be a really long branch, and the longest branch would be between orang and any of these. So between orang and human, or orang and chimp. So you take the midpoint right here at 3.5. So there are 3.5 changes along this lineage. There is 1 change along this lineage. There's 1 change from this node towards human, 1 change towards this node from towards chimp. Okay, and so you have to be very careful of what tree you're actually looking at. So this is a rooted cladogram where the branch lengths don't mean anything, right? Whereas this can also be represented as a rooted phylogram, where the branch lengths can be represented as the number of changes that have happened along each lineage. Okay, this is, I think, repetitive material, but this is a phylogram where the branch lengths actually mean something. So for example, your neighbor joining tree and even this particular tree will have you have branch lengths. Here the branch lengths are the number of changes that have occurred on each branch, and here it will be the genetic distance between these species, right? Alternately, you can have a phenogram or a dendrogram, which can be obtained using a UP geometry, and it sort of looks like a cladogram. But remember that it assumes a molecular clock. Just because all the species line up with each other, it doesn't mean that it is a cladogram. Okay, so you have to be careful with this. So this assumes a molecular clock, and all the species are at the same root, same distance from the root. Whereas here, the branch lengths don't mean anything. Okay, so what we will do, I think, what will be better for us to do?
Sir.
Yeah.
Sir, what does the in phylogram number of changes that is occurring? What does that mean actually? The number of changes.
So here you see number of changes that have occurred. So there are 4 changes that have occurred here.
So four substitution. I mean four bases have been 4 bases have been substituted.
Yeah. So 4 events in order to explain this character distribution given this tree.
Oh, okay.
Okay. Yeah. Okay. So I think what it would be even more clear if we actually start, if we do this by hand. It will not take much time. So let's say you have 4 taxa, W, X, Y, and Z, and we have time on our hand. Why don't we actually start, doing a parsimony tree? So you will have 3 possible tree topologies right here. So between yourselves, you can, kind of segregate who takes which tree. And why don't you tell us about how many evolutionary events are there in each tree in order to explain the current character distribution? Can we do that right now? I'm going to leave the screen on so that you can see the data. So you decide which tree you want to work on, and then start mapping the changes. You can also refer to the slides that were sent on the WhatsApp group by Chaitanya. If you want to, go through again how the mapping is done, but I hope it is clear. So I'll wait for you all to tell me how many changes there are for each of these trees.
So tree number 3 looks like no one has picked it yet. And people who have picked a particular tree, just get in touch with each other.
Alternately, I can read out and assign a particular tree to a bunch of people. No, that'll be too much. Just figure out what tree you want, which is your favorite tree, and do it. So remember, if you're taking, let's say you're taking tree 2, you just have to map, instead of the taxa name, you just have to put the character. So for example, it will be C here, Y has G here, and then there'll be a C here and A here. Has anyone finished?
Tree number 1.
Tree number 1, how many changes?
9.
9?
Yeah.
But Prashant says 11.
Yeah, even I got 11. Okay, maybe you would want to check that again.
Let me check.
Yeah. So site number 3 and site number 6, there will be 0 changes. So
11.
11. Yeah,
I did not count the second position.
Okay.
Yeah.
Yeah. So 11 for the first is correct.
Neha has also got 11 for tree number 1.
Okay.
Those of you who have already finished tree number 1, try tree number 2 and 3. Okay. Shubham says tree 3 is 13.
Correct.
Anju also says 13 for T3. Okay, people, what about tree 2? Those of you who have finished 1 and 3, try tree 2 also.
I think tree 2 was the least preferred among all of them.
Roy, don't give it away.
Is it 15?
No.
Krishnendu says tree 2, 10.
No.
So the way I
13. Suvendu says 13.
13.
Tree 2.
13. 13.
13. Correct?
Yeah. 13 is correct. Yeah.
Okay.
So the way I see it, you need at least 11 changes for this data set.
Yeah. So it's 13 for, so it's 11 for tree 1, 13 for both tree 2 and tree 3. So your most parsimonious tree is therefore tree 2, right? Yeah, I shouldn't be doing this in online sessions.
Roy, please.
Okay. So I'll just carry on. This is like the last slide, and then we'll start off with
Roy, just 1 minute, 1 minute. Can you go back and give the numbers again so that everyone gets it?
Yeah, so tree 1, 11, tree 2, 13, and tree 3, 13.
So the most parsimonious tree is tree 1. So those of you who have not tried it, please try it. Yeah, Roy, carry on.
Aniruddha?
Yes.
Joyito, yeah. So which one is, I think the least one is the most parsimonious, right?
Yeah, so your the tree that has the least number of events.
So that will be 1.
Tree 1, correct.
Yeah, that's the thing. You say tree 2.
No. Oh, man. Okay, so there was a sorry.
Okay.
Okay. I'm sure you realize that with every tree building method that we've been dealing with right now, so the methods have slowly become, more and more better, right? In order to try and get to the right, what we think is the right phylogeny. But all of these tree building methods, almost all of these tree building methods have their own, drawbacks. So one of the main drawbacks of parsimony is that it does not account for, so homoplasy can be a problem. So right now, given the data set that we have, it assumes that all of these are shared derived characters, right? But it cannot differentiate between a shared derived character and a homoplasy. It also does not correct for multiple hits. So basically, you cannot use a model of sequence evolution in parsimony, whereas actually in neighbor joining and UPGMA, you can use a model of sequence evolution, because you remember we're dealing with distances there, genetic distances there. So you can actually use corrected genetic distances to come up with your NJ and UPGMA tree. So parsimony is not able to deal with the problem of multiple hits, which models take care of. Also, searching for an optimal tree, there might be a computational limitation, especially if you have a large number of taxa or a large number of characters. But most computers these days are able to handle an exhaustive search, or basically search all the trees, all the possible trees. But one thing that we're not talking about in this workshop is that many of these programs actually do these small tricks in order to reduce the number of trees that it has to look at, right? One way to reduce the number of trees is obviously look at only unrooted trees, right? But even within unrooted trees, you can still, if you increase the number of taxa, your number of unrooted trees are also going to astronomically increase, right? So there are tricks that many of these programs do in order to reduce the number of trees that it is actually checking out. And these methods are called heuristic searches. Okay, so there are also obviously a lot of advantages in parsimony, and it's very similar to a cladistic approach that we had done on the first day, and you can actually map changes on the branch using the principle of parsimony. So that actually makes it much more intuitive. So although you can't incorporate a model of sequence evolution in maximum parsimony, one thing that you can do is you can account for the transition transversion ratio. So you can do that using a particular weighted matrix where you can specify how much you weigh transitions over transversions. So you can find out the transition transversion bias in mega, and that information you can actually use to correct for this transition transversion bias. Okay, so if there are there any questions at this point? If there are nothing, I'll just switch to the practicals.
I just wanted to add that the alignment that Roy has shared with you, use that alignment to also build a UPGMA tree. And we can discuss it tomorrow if we have time. So use the same alignment to build a UPGMA tree and then compare it with your parsimony tree.
Okay, I will be dealing with Partition Finder. So one thing that we were, Praveen, Chaitanya, and I were thinking is that instead of all of you actually doing the practicals side by side, what we could do is I'll just run over the different methods that we will follow in the practicals, and I will send you the video so that you can actually try it out, and you can use the video as a tutorial and try it out later. So if any of you think otherwise, please let us know, and we can actually do a hands-on session. One thing that I wanted to show is how you can actually make a FASTA file from a current alignment, right? And for that, I also wanted to show you an important website. So let's say we take the primate file that Chaitanya had given you, and I'm going to click on the mass file, which has the alignment. So this is the alignment of primates, cytochrome B. This is already an aligned file, and just in case, I'm going to align it again. And you can either use this thing called muscle, or you can use cluster W. Okay, once it is aligned, I can actually change this alignment into a FASTA format. So all I have to do is go into data. There's an option called export alignment, and I select FASTA format, and then I save it wherever I want to save it. Okay, the reason why I'm telling you this is that this FASTA format is acceptable in multiple programs, and it's basically acceptable cross format. So it might be important for you to understand how to actually change your mass file or your alignment file into a FASTA file. Did someone have a question? Because I thought I saw the, I thought I heard something.
I had.
Yeah.
Yeah, but my mic wasn't on. Okay. So my doubt was, when do you use the muscle or cluster W? How do you decide which one you have to use?
So I mean, from the time muscle, the earlier versions of Mega had only cluster W, and muscle is apparently much better, especially in dealing with gaps, where cluster W had a few issues. So there are a few papers out there, and which say that muscle is definitely much better than cluster W. So from the time that muscle has been available, we have been using muscle to align the sequences, and it's worked just fine. But in any case, I what we would all recommend is that even after aligning the sequences using muscle, you actually check the whole the sequences by eye.
Okay, so basically I process my file through muscle and then I process my file through cluster W, will I have a difference between both?
So till now, I haven't noticed any difference, but maybe the kind of data that we have fed in Mega to use both muscle and cluster W doesn't really have any complications that may be created by both these methods. And we actually don't understand how different these algorithms are. So I don't think I will be able to help you there. But by and large, muscle has been doing a great job.
Oh, okay, thank you.
Okay, the reason why I showed you that is because there's, in fact, you can try this out right now. If you just Google POSADA and alter, so POSADA space ALTER, you'll get this website called www.singgroup.org. So I would recommend that you keep this particular website bookmarked and handy if it opens. Is everyone able to hear me? Am I audible?
Yes, you are.
Okay.
Yes, you are. And the problem is with the website.
Okay. So none of you are able to open it, is it?
Yes, I am not able to open.
Okay. So I'll get back to that later on. What we'll do is we'll start off with I'll start off with Partition Finder. So we've talked about the models of sequence evolution today, and what we were so one of the programs that we were using earlier to find out the best model of sequence evolution was J model test, right? But in J model test, you had to individually feed every data set. So, for example, if you're using two different genes, let's say you're using 12S and you're using ND2. So you'll have to feed the 12S gene data set to it to J model test and find out what is the best model of sequence evolution. And then we'll have to feed the ND1 or ND2 data set to it and find out the best model of sequence evolution. So then you have both this information. But what the good thing about Partition Finder is that you don't have to feed these data separately, right? So we'll see how that works. So what I'll do is I'll go into Partition Finder, and the file that we will be working with is inside Partition Finder examples, and there's a folder called Nucleotide. So there are these two files here. One is called test, and you'll notice that it is a phylip file, phy, right? What I was about to do is go to that website alter and convert the FASTA file into a phylip file, right? But we've already someone has a question.
Yeah, Aniruddha, I have a suggestion and a question. Suggestion is, if the website is not working, what I do is I use Genius, the free version, trial version, and even if Genius 14 days they gave, after the 14 days also you can convert the format easily throughout FASTA, Nexus, Phylip, and there are lots and lots other format also that you can do it, and you do not need internet. And secondly, I just wanted to ask you, because you are telling that in Partition Finder we are feeding more than one gene or two gene, three gene, four gene, whatever. So before that we need to concatenate the data, right?
Yes. Before that, we need to concatenate the data.
So do you do it manually, or is there any, like I have FASTA files of 12s and then I have FASTA files of ND2. So can you is it there? How will you tell me how to go about the concatenation of data?
I can show how to concatenate data maybe after I show the partition finder.
Okay.
But right now, let's just work with. Let's just assume that I've already concatenated it.
Okay, fine. Thanks.
What's important is even after concatenation, you need to know from which side to which side is what gene. So we'll get to that in a bit. So here, the important files right here, there is one Phylip file, and there is another file called a CFG file, or that is a configuration file. So your Phylip file, you can open the Phylip file using WordPad or Notepad. So if you open it, it's basically your data, right? And it says that there are 4 species in it. There are 4 taxa in it, and the total number of total number of sites are 2,208. Okay, and this Phylip file is called test. And there's a reason why I've actually said this, because this configuration file called the CFG file, the Partition Finder file, is where you will actually configure your analysis, right? So if you can open this using WordPad or Notepad or any text editor, and you have to make sure that in this particular line where it says alignment file, your alignment should be named exactly as the file that you have, the Phylip file that you have. If you have any changes here, it will not be able to recognize. Okay, so I'm going to leave all these other options unchanged. There is a manual associated with Partition Finder, which actually talks about all these different options that there are. So I'm not going to talk about this, just go through the manual. What's important here is that you can either so you have models of evolution. You can have either all, which would mean all possible models, or you can have models only for Raximal, and we will deal with Raximal tomorrow. But the reason why it says Raximal separately here is because the current GUI version, or the graphical user interface version of Raximal, can only take GTR and its variants. So it can't take any other model. Similarly, Mr. Bayes also separately, because Mr. Bayes, without any kind of tweaking, you can actually fit in only 5 different kind of models. Mr. Bayes and Beast, you can fit in 5 different kind of models, right? So here I've put all, right? And this is how your model, your best model, gets selected. So you either have an AIC or a BIC. AIC stands for Akaike Information Criterion. BIC stands for Bayesian Information Criterion. It's just a criterion to find out which among all the models that you've tested is fits your data set the best. And this is the most important part, where you actually feed in the different partitions that you have in the data set. So right now, I know that in the data set that I fed in, which is called test.phy or test.phylip, there are 3 different genes, right? And all 3 genes are protein coding genes. And I'm with this particular line, I'm saying that my gene number 1 is from 1 to 789, and it's a protein coding gene. So therefore, I'm partitioning not just the gene, but also each position separately. And then my gene number 2 is also a protein coding gene, which is why it's there are 3 positions, 1, 2, and 3, and it is about 600. So this is about 659 base pairs. So 790 to 1449 is 659 base pairs long. And gene number 3 is also a protein coding gene, and therefore 3 different partitions for all the 3 positions, and it is about 758 base pairs long. Okay, so this is all the information. It's an exhaustive information that I have currently of all the of my data that I have fed it. Okay, and so there are some other methods that Partition Finder uses in order to find out the best partition and the model. So you leave all that by default. So if you just remember that if you make any changes here, don't ever save as. So if you do a save as, the format will change. So you just make whatever changes. I would suggest that just like Chaitanya did yesterday, just make a copy, make whatever changes you need to make, and then save. So then the format remains just like that. Okay. All right. So in order to run this, it's a little bit of circus that you have to do in order to run Partition Finder. So I'll just run over what you have to do. First things first, you have to call the command prompt window, right? And your Partition Finder will work only if you have specified Python. So for example, if I type Python, then this something like this should come up, that Python 2.7.5 or something, that if it says that Python not found, then it is not going to work. Okay, so the first thing that I need to do is type the word Python and put a space, and then I drag and drop this particular icon called Partition Finder, which is a Python file. I drag and drop this right here. Okay, and then I put one more space, and then I go into where the folder where my data is, which is right here in Nucleotide, and I drag and drop this particular folder. Okay, that's all. You hit enter and nothing happens. Of course. Okay, I'm going to try it again. Okay, I don't know why the previous one did not work, but I just basically did the same thing. And now it has started the analysis. So it's basically going to, given all the information that you have given, you have fed in Partition Finder, which is your complete concatenated data set, where you specified from which site to which site is what gene and what position and all that. What Partition Finder is going to do is it's going to test all the possible models and tell you how many of these partitions that you've actually fed can be clubbed together. In other words, it says, okay, so these partitions, this partition number, so right now I've fed for so 3 protein coding genes. So I've fed how many partitions are there? 9 partitions. Yeah, so I have 9 partitions to start with, and what it's going to say, what is going to tell you at the end of the analysis is how many of these partitions evolve in a similar manner. Right? So then it can reduce the amount of partitions that you have, thereby reducing over parameterization. Okay. We're almost done here. Okay, so we are done. I'm just going to minimize this. So what you can do is after you've run the analysis, is if you go to the nucleotide folder where your configuration and file were, you will realize that magically 2 more files have appeared, one folder and another log file, and there'll be a folder called analysis, and within analysis there will be a file called best scheme. So if you open best scheme, I'm just going to increase. Yeah, I hope everyone can see this. So what it's saying is that it's tested against all these different models and the variants, right? And it says that out of so it can actually put together the 9 different partitions that I had given into 4 partitions itself, where each partition, each of these partitions, it also suggests what model to use. So my partition number 1 will have gene 1 position 1, gene 2 position 1, and gene 3 position 1. And it also tells you that the best model for these positions is F81 plus G. So this is my partition number 1. Right? So F81 plus G is the best model. Partition number 2, F81 plus G is the best model, but the partitions are different. And then you have partition number 3, where you have a completely different model. And then partition number 4, also very different. Okay. And it also gives what's really cool is it also gives you one Raximal style partition definitions. I'm not going to talk more about this, but it gives it in a format where you can actually copy and paste it directly in Raximal. So that way it makes it life much easier. Okay, so that's it. That's about Partition Finder. So do any of you have any doubts?
So they have given three sets of model. They have mentioned 3 sets of model. So which model we will choose for further analysis?
So it suggests. So remember that you had. So in my data set, I had given 9 partitions in total, right? So what it's doing is it's combining a few of these partitions together, basically saying that these partitions evolve in a very similar manner. And for these partitions only, you choose this particular model. As a separate partition, or only these, you club only these together and have this model, which is very similar to this, but your partition is different. Again, for this one, your partition is different and you have a different model. This is different. So does that answer your question?
Okay, but in J model test, they specifically, they suggest only one type of model. I think.
Yeah, but remember that in J model test, you are only giving one data set.
So if we want to do 2 gene sets, we have to first give the data of one gene, then next gene, like that. Then we should find the model.
Yes, that's right.
So
and Yeah,
So
and
how
also
will we do it when we concatenate? We actually concatenate those two gene sets before doing the Raxamel of Mr. Way, something like that. So how will we if it is giving two different models, how will we do it in a better way?
for different partitions, different models, setting different models.
I know here the different here it is showing that different partition has different models, no? But
Correct.
in J model test, we will get only one model. I mean one model. Am I right?
So yeah. So which is why we are not using J model test. Because we think that Partition Finder is much better because you can actually feed in a concatenated data set rather than individually giving each data set. Also the other good thing is that in J model test, I don't think you can actually even for each gene, even if you know it is protein coding, you cannot partition it based on different codon positions. Right?
Okay.
Whereas,
but many papers I have seen, many papers they have done with J model test, and they have used two or three different genes also. So how come that is possible?
they would have done it separately.
Separately,
But
J
yeah,
model test they have done separately, and for doing the Raxamel as well as Mr. Bayes analysis, they have concatenated data.
yes.
So okay, fine.
Roy,
Yes.
here.
Yes.
Just I wanted to know that these models that it has generated, like AF81 plus G and all. So for RexML, if I go down and see the RexML, they have not specified a specific model because RexML only have 4 or 5 models available. So in between that 4 or 5, is there is this model test will find out which is the best one?
So in Raxamel, you only have GTR and its variants.
Okay.
So what I do is I just select GTR gamma I.
Okay.
Which assumes that obviously it has separate parameters of substitution from one base to another base. It assumes that each site is evolving differently. It also assumes that there are invariant sites, which means that all these characters, all these parameters are actually going to get estimated, right?
Okay.
But yeah, but but the somebody can point out an issue saying that okay, there are just too many parameters for a small data set. That is an issue that you will run on into, especially in a program like Raxamel. But I also wanted to point out that there is another version of Raxamel available called Raxamel Next Generation, which you can run, which can be run only using Linux and Mac, where you can actually specify models other than GTR and its variants.
Okay.
The only issue is that it's a command line based program, but at least you have the option of so if you run this data set using model test or partition finder, and if it suggests a simpler model than GTR, I think you should go for a simpler model on any day.
Okay, thanks.
Hello. I have one question. Like if I have a if I have to build a tree of a single gene from many samples.
Yeah.
Then can we use this partition finder thing?
Yeah.
Or it's not required?
Yeah. So for example, if your single gene that you are using is a protein coding gene, you will still have 3 different partitions, right? So you'll have position 1, position 2, and position 3. And maybe after you run it in Partition Finder, maybe Partition Finder is going to say that position 1 and 2 are evolving in a very similar manner, whereas position 3 is evolving in a manner which is very different from position 1 and 2. So that way you reduce the number of partitions and also get a model for each of these partitions.
Okay. Yeah.
Hello, Aniruddha. This is Shubham here.
Yes.
Here, the models which we are talking about, we'll be knowing more about them further, or what are these? I don't understand the whatever the F81 or GTR, whatever the name is.
Oh, so see, I started off with Juke Scanter, right?
Yeah. Okay.
And because it's probably the easiest to explain because you know what assumptions there are.
Okay.
And like I said, with as and when you keep increasing the number of variables or the nuances, you can get more and more complex models. So right now there are I think there are about 1,800 different models, which means that there are so many nuances that are possible.
So each model will be a set of assumptions and
a different set of assumptions and parameters.
Yeah. Okay. Got it. And here, this program is just going to tell you that which will be the best model. It is going to estimate. It is not actually going to run it, right? That's what
No. So running it and how models are important will come later tomorrow when we talk about likelihood, and when day after tomorrow Chaitanya talks about Bayesian. So their models are going to be incorporated.
Okay. So this particular program is just going to estimate that this model is going to be the best one for this particular gene.
Correct.
Okay. And what if this program somewhere there is a loophole, and how do you know? Okay, this program goes wrong here.
How do I know whether the program is going wrong?
Yeah, if that's possible.
Well, I mean, I'm not sure how to answer that. So
no, so see, if there is some particular gene and you know about it, but there are you have a lot of different models, and you know, this is the correct model, but the program shows something different.
But how will you know if this is the correct model? Because it's going to be very because these models have lots of different parameters.
Okay.
I don't think it is possible to do all this manually.
Oh, yeah.
For a simple model like Juke Scanter, it is okay because the only thing you need is the p distance, right? But with other models, there are a lot of different parameters that need to be estimated.
Okay, but
so yeah,
just only on one program we can't rely. No, there should be some backup or something like that. Or is it very robust so that we can rely on it?
Well, we are assuming that this is very robust.
Okay.
Can you please show the concatenation thing?
Okay. Okay, one sec. Okay, I'll just have to prepare it. Give me a couple of minutes. I'm just going to put my screen, stop presenting. So if you have any other questions, maybe you can ask Praveen or Chaitanya. I'll just give me a couple of minutes.
Yeah, I'm around. Praveen has been locked out of the meeting and he's not able to join back. I think some internet issues at his place. So
okay.
Yeah, if you guys have any questions, you can probably ask me when Roy is not around.
So if we have multiple models have been suggested by the partition finder for a concatenated data set, which model will we use?
We'll use all of them.
Okay.
Right? One model for each partition, or one model for whatever partitions that Partition Finder suggests.
So, but we will get maybe multiple trees along with that. So how could we?
We will get a single tree, right? But the deal is that if Partition Finder says that use 3 different models for 3 partitions, it's going to treat each partition separately, okay, and apply those models on those partitions, just those partitions, right? but the tree that you get in the end will be one single maximum likelihood tree. So it is, see, the idea is basically to not treat all your data the same way. Okay, let's say you're using one gene, one protein coding gene with 3 codon positions in it. We all know that position 3 evolves faster than 1 and 2, and position 1 evolves faster than 2, right? So the deal is to not treat these 3 positions the same way and treat them differently, because evolutionarily they are different, right? So that is the reason we use different models for different partitions. So, or for example, you could have concatenated a mitochondrial gene and let's say a nuclear gene, right? Mitochondrial genes evolve way faster than nuclear genes. So it is better to treat the mitochondrial gene separately from the nuclear gene, because the nuclear gene is, it's not going to evolve as fast as the other one, right? So the idea is to not like treat everything the same way, to get a more accurate, enumeration of evolutionary relationships. That's the whole idea, right? What about non-protein coding? You treat the whole gene as one partition for a non-protein coding gene.
Suppose I have a large data set, like I have some 50 or 100 sequences of a protein coding gene. So I have to concatenate all the sequences or what?
Sorry, I lost your question. Can you just repeat that?
Suppose I have a big data set, like I have some 50 or 50 sequences of a single protein coding gene.
Okay.
Then I have to concatenate all the 50 sequences.
If you have only one gene, then there is no question of concatenation, right?
If it is a protein coding gene, like
even if it's a protein coding gene, so you'll have one sequence per gene per animal, right? So you
suppose I have different haplotypes, like I'm getting that gene from different individuals, and I'll get different sequences.
Okay. So where is the question of concatenation?
Okay. Like if there are different genes altogether, then only we should concatenate.
You concatenate only when you have more than one gene, right? Otherwise, it's an alignment of 50 sequences, and that's that.
Okay, fine.
Yeah, but I'm not sure if I understood your question, Dipanvita.
Yeah.
So typically, as Chaitanya pointed out, you sequence one particular gene from, say, a bunch of species that you're interested in, right? And,
no, from a single species.
Okay, so within single species, many individuals of the same species, right?
Yeah.
Okay, so you have again one particular gene that you have sequenced from multiple individuals of a species. So where is the confusion here? I mean, so are you saying that there are different alleles per individual or something like that?
Yeah, like suppose suppose MHC gene, major histocompatibility gene, that is a multi-copy gene, and from the same individual, if I get 3-4 alleles.
Oh, okay. That is a different question altogether. So you have multiple copies of the same gene. Now, what you have to do, you have to treat each of those copies as separate genes. Okay. So when you have gene duplication event, one particular ancestral gene, duplicates, and you have multiple copies in the ancestral lineage, and those copies are retained in multiple species or multiple individuals within the species. So basically, one particular gene might have, say, 5 copies. So you have gene 1, gene 2, gene 3, gene 4. So you then concatenate each of those genes in all the individuals, right? And you make sure that gene 1 you make orthologous comparison. In other words, in your alignment, gene 1 from individual 1 is below gene 1 from individual 2, and so on.
Okay.
Right? So
Okay,
basically,
okay.
you treat them as separate genes. Okay, does that answer your question?
Yeah. All right.
Okay, so I have, can you see my screen? Is the folder visible with gene 1 and gene 2?
Yes.
Okay,
Okay,
all right.
Roy, hang on. There was one more. I think there were 2 more questions. What about non-protein coding? And then Ashna says, how do we assign partitions for introns? Were these addressed?
No, so if you have a protein coding gene, you have 3 positions, right? So the position 1, position 2, position 3, right? But for non-protein coding genes, you don't have 3 codon positions. So you just keep the whole thing as one shot. In fact, let me just assume that one of these genes is non-protein coding, so I can show you what the partition would look like.
Okay, I just want Roy, I just want to make a correction. We often make this mistake. So there's nothing like non-protein coding gene. Gene by definition codes for a protein. So it's a region that is either neutral or it has some other function, maybe some regulatory function, or so basically it is not coding for a gene. I mean, coding for a protein. If it is not coding for a protein, then we won't call it a gene. But as Roy pointed out, regions that are not coding for a particular protein are basically, either junk DNA, or it might be a neutral region, or it might have some other function. But because it's not coding for a particular protein, there is no question of further dividing the region into codons and first and second and third position of the codon, right? And then Ashna had something, how do we assign the partitions for introns? Yeah, so when you are looking at a nuclear marker, you first separate out the exons and introns, and then introns again, it's non-coding, so you don't have first, second, and third position. The whole intron is treated as one region, and then you try and find out what is the model of sequence evolution for the whole intron. Right, sorry, carry on.
Okay, so I have 2 different genes here, right? So this is my gene 1, right? And I have these primate taxa. There are 11 taxa, right? And the whole data set is about 1140 base pairs, right? So this is my gene 1, and I know that this is a protein coding gene. So this is a gene, so it's protein coding. So, and my gene 2, so this region is not protein coding, but what I have to do is I have to make sure the way my taxa are arranged are exactly the same as what was there in the previous file. Okay, you'll realize why I'm saying this. So, and both these you have to align separately. So the first file you have to align separately. This one you have to align separately. You can't align these regions once you concatenate them. Okay, so what I'm going to do is, because this is gene 2, yeah.
Roy, I have a question. Like, for example, the taxa number 3, Homo sapiens, for example, we do not have the sequence for the gene 2. We do have the sequence for the gene 1, but we do not have the sequence for the gene 2. So can we just keep it as blank?
You can keep it as missing data.
Throughout it's a missing data. Yeah.
Throughout it is a missing data. Yeah.
Okay.
Which would mean that the only information that you have of Homo sapiens is gene 1. Okay, is the partition one, right? So for this is the second.
So for missing data, we will leave that portion as blank. How will we align them as equal things?
So, for example, my first file, I had 11 taxa, right? And my third taxa was Homo sapiens, right?
Okay.
So let's suppose I don't have data for Homo sapiens,
Okay.
right? So let's say I don't have data for Homo sapiens, right? So I will first align this, right? This is align DNA, right? This is now aligned, and I will do all the whole circles. I will check whether the alignment is done properly and all that or not. And I have made a list in the previous file. My third taxa was Homo sapiens, right? So what I'll do is I can click on any base here in the beginning, and if I press Control plus N, you can actually add one more sequence. So I'm going to keep it as Homo sapiens, right? And here I'm going to just put question mark. Okay. So it will have to be question mark throughout. All right. So let's assume I'm putting I don't have patience to make sure the question marks for 993 base pairs. But yeah, so let's assume that there is missing data for this taxa completely, right? So now what I'll do is I'll just click on any base, Control A, so all of them get selected, and then I copy this with Control C, and I can actually close this, and I open gene 1. I open this, I go right at the end, right at the end, and I click on this particular space on the last, and I paste my data, which is Control V, right? One thing that you have to make sure is know where one from your first gene starts from. So my first gene is from base number 1 to 1140. So that, and my second gene is 993 base pairs long, so therefore it will be 1141 to 2133. Okay, so you have to make sure you have that information. So if I have to partition this, so my gene 1 position 1 would be base number 1 to 1140 3. What was the total? Okay. So okay, does this make sense? So I'm just basically saying that I have two genes, I have two regions. So my first region is a gene, and it codes for a protein. So there are 3 positions: there's position 1, position 2, position 3, and I am partitioning all these 3 positions separately. And my second region is not a protein coding region, and therefore it is only just from site number this one to site number this one. I hope that makes sense.
Yeah, this can be done for introns.
Okay. Yeah, I think we are done. Is there anything else? No more questions?
So when we are concatenating the gene sequence, do the position of the placement of this gene, I mean the order of this sequence will affect the tree topology or something like that?
The order of the genes, like the different partitions?
No. When we are concatenating them, for example, first we place the ITS region, then comes the LSU region, and comes the small subunit. So if we use different permutations, will that affect the tree topology?
No, it will not affect the tree topology at all. But you just have to make sure before you concatenate, you will have to align them separately. And once you concatenate them, you shouldn't be, you can't be doing a communal alignment because you have three different regions.
So do we have to concatenate all these sequences manually, or there are automatic programs, algorithms to do the work for, say, large data sets?
I always prefer doing things manually. I'm not sure if there are any other programs that can actually do it for you.
Yeah,
but
there is a there is a program called Mesquite that I know of, and which can be used to concatenate different alignments. So you can just look it up. Yeah, if we find the information, we'll send you the link. Roy, sorry, you were saying something?
No, I was saying it's. I mean, I always felt it was better to actually do these things by hand, so that you know what you're doing.
Yeah, I completely agree. I think that's a very important point that Roy is raising. You should look at your data set and make sure the alignment is okay, and do these things by hand if possible, because it gives you a feel of what the data looks like, right? But what has happened today is with large data sets, everything has been done using some program, and you don't see your alignment, and that is, I'm not very comfortable with that situation.
Okay, so if there are no more issues or doubts, should we just call it a night?
Yeah, before we do that, so I guess everyone has been given these data sets, right?
Yeah.
So people, please try out Mega, build trees, do the routing and all that stuff, and you have the whole day tomorrow. And if you have any issues, let us know. The only way to understand a lot of these concepts is actually doing them by hand. So I would highly recommend that you spend some time actually, looking at the data, doing some analysis. And Roy also gave you a small alignment, with and asked. We did this parsimony exercise today. Those of you who have not had a chance to do it, I would highly recommend that you do it. Use the same alignment and build a UPGMA tree. This will really help you understand what tree building is all about. Unless you do it by hand, you're not going to get a hang of it. So take the time,